Welcome to This Explainer. Today, we're diving straight into the invisible mechanics behind our digital lives. We're talking about how we solve the ultimate data bottleneck. I mean, think about it. Every single time you load an image, stream a song, or download a massive file, you are heavily relying on these invisible mathematical frameworks. They're constantly working behind the scenes to squish gigantic amounts of information into tiny, manageable packages. And today, we're going to explore two absolute titans of this field: the Huffman and Lempel algorithms. So ask yourselves this crucial question: how do we fit infinite data into finite space? Compressing massive amounts of information is exactly what these two foundational source coding algorithms were built to do. Our digital universe is literally expanding at an exponential rate, but our bandwidth and our physical storage capabilities, well, they're fundamentally finite. To bridge that gap, we don't just need bigger hard drives, we need way smarter math.
Here is exactly how we're going to break it all down today. 1. The data compression problem. 2. Huffman, the probability game. 3. The flaw in the system. 4. Lempel, the pattern spotter. And finally, 5. Powering our digital world.
Okay, let's jump right into section 1, the data compression problem. The overarching goal of any source coding technique is really quite simple: represent information using the absolute fewest possible bits, but without losing the original meaning of the message. To actually compress data effectively, and this is key, without totally confusing the system later, we use a prefix code. This concept is a real game changer. A prefix code guarantees that every variable length code can be translated instantly. Imagine you're a computer trying to decode a stream of zeros and ones. If 0 meant A and 01 meant B, and you suddenly received a 0, you'd be stuck. You wouldn't know whether to stop at A or wait a microsecond to see if a 1 comes next to make it a B. A prefix code totally eliminates that ambiguity. Basically, no code word is allowed to be the starting part of another one.
Moving on to section 2, Huffman, the probability game. Let's meet our first protagonist, an incredibly elegant solution introduced by David A. Huffman way back in 1952.
Huffman was actually just a college student when he developed this algorithm for a term paper, and he completely revolutionized information theory by figuring out how to build optimal prefix codes. His algorithm works kind of like a meticulous statistician building a custom alphabet from the ground up. First, you take your entire set of symbols and rank them by how likely they are to appear. Next, you grab the two least likely symbols, tie them together into a new node, and assign a 0 and a 1 to the branches. You just keep repeating this process until you reach a single root, building a sort of tree. Then, to find your final code, you literally just trace the path from the root back down to your symbol.
The brilliance of this is how the most frequent symbols get the absolute shortest codes. Take a symbol we'll call x1, for example. If it has a really high probability, say popping up 37% of the time, it gets assigned a tiny 1-bit code word, just 0. But a rare symbol, let's call it x4, which maybe only appears 7% of the time, gets handed a much longer 4-bit code, like 1110. It's incredibly optimal because you're saving precious space on the characters you use the most.
Which brings us to section 3, the flaw in the system. Because, well, even the most meticulous statistical models have a breaking point.
While Huffman coding is mathematically beautiful when the conditions are perfect, the real world rarely hands us perfect conditions. Here is the fatal flaw. Huffman coding absolutely requires knowing the text's statistics in advance. To build that perfect little tree we just talked about, the algorithm needs to know exactly how often every single letter or symbol will appear across the entire file. Now, for a short, static text document, sure, you can calculate that. But for a massive, continuous live stream of data, calculating those probabilities in advance is literally impossible. It's totally impractical for real-time applications. But then, a radical new approach completely changed the game by eliminating the need for prior probability knowledge altogether. Think of it this way. If Huffman is a meticulously planned blueprint, our next algorithm is more like an improvisational jazz musician, just adapting on the fly. And that brings us to section 4, Lempel, the pattern spotter. Enter Abraham Lempel and Jacob Ziv in 1977. They treated compression not as a rigid probability game, but as adaptable pattern recognition. They realized something super important. Human data, especially language, isn't just a bunch of random letters. It has memory. Instead of doing heavy math up front, Lempel acts like a dynamic shorthand dictionary. Think about the English language. The letters TH or ING
cluster together all the time, right? Lempel-Ziv capitalizes on this. It parses sequences into variable-length phrases and builds a dictionary as it goes, requiring zero advanced knowledge of the source file.
It actually builds this numbered dictionary of prefixes in real time. It represents new phrases simply by pointing to a previous string's location, plus just one single new bit. So let's say it's already seen the string 0, and then later it sees 0, 1. It doesn't waste space writing out the whole string again. Nope, it just jots down the dictionary location for 0 and tacks on the new 1. As the document gets longer and longer, entire massive phrases just become small numerical indices.
And let me tell you, this method is insanely effective. It achieves a massive 55% compression rate on standard English text. Just think about that. Over half of your file size just shaved off purely by recognizing that language repeats itself and taking advantage of those patterns as they emerge. When you compare them side by side on English texts, Lempel-Ziv's 55% clearly outperforms Huffman's 43%. And the why is fascinating. Huffman treats every single letter independently based on its overall probability. But Lempel-Ziv, it leverages the interconnected nature of human language. It remembers that words have structures, and it compresses those structures holistically. Finally, Section 5, powering our digital world. So where do we actually encounter these two invisible giants today? You might actually be surprised to learn that neither of these algorithms was lost to history. In fact, you've definitely used both of them multiple times today without even realizing it. Huffman coding is what helps compress your JPEG photos. On the flip side, Lempel-Ziv powers your Unix systems, and its variants, like LZW, are literally what make GIF images possible. Even the PNG format uses a variation of Lempel-Ziv to keep file sizes incredibly low without losing visual quality. It is absolutely fascinating how mid-century mathematical theories became the bedrock of modern digital media. Think about it. A college paper written in 1952 and a theoretical framework developed by two researchers in 1977, they literally just sat waiting for computing power to catch up. And then, boom, they exploded into widespread adoption in the 1990s to build the internet as we know it today. Claude Shannon, the father of information theory, famously said, "I just wondered how things were put together." And that's really the heart of it. Much of this genius wasn't driven by some rush to build consumer products. It was pure, simple curiosity about how our world connects. How small can we make a message? How much redundancy is just hiding in plain sight in our words and images? So I'll leave you with this final thought to ponder. If we evolved from Huffman's calculated probabilities to Lempel-Ziv's dynamic patterns, how on earth will we compress the infinite data of tomorrow? With the massive rise of AI, giant language models, and 4K streaming, our thirst for bandwidth is only getting bigger. The next great breakthrough in compression is out there right now, just waiting for someone to wonder how things are put together. Thanks for joining me on this explainer. Catch you next time.